This is Cycle 1, Lesson 2, and we're going to continue working with polynomial functions. Today we're going to look at how we can use transformations to graph polynomial functions. You learned about transformations back in grade 11, and we're going to do a lot of more work with transformations, especially in this cycle, but all throughout this course. There's a lot of graphing in this course. So last lesson, we looked at what was called a power function. It's the simplest type of polynomial function. It's in the form f at x equals a times x to the exponent n. So it's just a single term. We look at the exponent, the n, that tells us what degree the power function is. So if n is 2, then it's degree 2. It's a quadratic. If it's degree 3, then it's a cubic, and so on. A polynomial function has the form shown here. F at x equals a subscript n, x to the n, and a subscript n minus 1 times x to the n minus 1, right down to a to the 0. That's confusing when you look at it that way, but let's take an example to maybe clear it up a bit. Let's say we had a quadratic, then a to the n would just be some coefficient. It could be anything. Let's say it's the number 7. It could be -5. It could be anything. And then we've got x to the exponent 2. All right. Then we have the next term. That would be the coefficient of the next one. That would be a to the n minus 1. Again, that can be anything at all. So maybe, just to pick a random number, maybe it's 11, and then we go down 1 maybe for the exponent, so that's x to the 1, which we wouldn't normally put the 1 in there, but I'm doing it just for the sake of writing it in. And then the next one would be our constant term. That's our a to the 0 here on the end. It could be, let's make this one negative just to change things up a little bit. It could be, say, -5, right? So the constant term, just like you've got on the right-hand side, a to the 0 is just a number without an x in there. The highest term, the one on the far left, is our leading coefficient. And you can have all these terms in between. So for a quadratic, the most terms we can have is 3. Exponent 2 and exponent 1 and a constant term. For a cubic, we could have 4 terms. We could have exponent 3, 2, 1, and constant, so on. So n is the whole number. It's a whole number. It's the exponent. X is the variable. The coefficients are real numbers. Remember, real numbers can be positive or negative. They can be decimals or not decimals. It doesn't matter. They could be fractions. The degree is the exponent with the greatest power. If it's written in standard form, it's the one on the left. That's called the leading coefficient. And a sub 0, or a naught, as we might call it, is the term without a variable. It's the constant term. So let's fill this in together. So I'll get rid of this for a moment. And let's just look at some functions. So if we have an even degree with a positive leading coefficient, remember what that means from last period. If it's an even degree, it's going to be like a parabola. A parabola, a quadratic, is our lowest degree type of even degree one. So let me just sketch a little Cartesian plane. So all even degree functions, polynomial functions, are going to be like a parabola. So they're going to have a U shape. If it's got a positive leading coefficient, that means that it's going to open upwards. It's a parabola shape opening up. It might be degree 4, it might be degree 6. It's going to be a variation on the parabola. Degree 4 is going to be a bit boxier. Degree 6 will be boxier still. 8 would be boxier still. You know, we could have degree 20. But as long as it's an even degree with a positive leading coefficient, it's going to be a parabola opening up. And remember, for our quadrants, it's going to go from quadrant 2 to quadrant 1. Again, we're leading it, or we're following the graph from left to right. So we start in quadrant 2, and then we end up in quadrant 1. And that's what this is saying here. That's the end behavior. Another way of saying this is, imagine that we're looking at the x-axis. Imagine that we are starting here at the origin, and then we go out towards negative infinity on the x-axis, right? That's what this is saying. Go towards negative infinity. What's happening to the y as I go this direction? Well, as I go that direction, the graph is going up. So that's what this is saying. So it's another way of writing this. It's saying as x goes towards negative infinity, y is going up to positive infinity. And then as x, again, go back to the origin, as x goes towards positive infinity out here on the x-axis, that's what this is saying, well, we're also going upwards. Y is going up for this one as well. So this is a more formal way of writing the end behavior. For now, let's just focus on from 2 to 1, from quadrant to quadrant. You'll notice that for the other ones below this, I've already got it filled in. I'm not going to make reference to it right now, but you can look at them and see if they make sense to you if you want to. We're going to come back to this more formal way later. All right, even degree, negative coefficient. Well, again, even degree is a parabola shape. Leading coefficient negative means it opens down. Whether it's boxier or less boxy, it's going to be like this. And that's going to go from quadrant 3 to quadrant 4, right? Because we're starting at the left, and as we go this way, we end up going from 3 to 4. So Q3 to Q4. And if you want to check that, what's beneath that, and see if that makes sense to you, then you can. Odd degree. The most basic odd degree one would be linear. That's a degree 1, which is odd. But there's also cubic or quintic, so degrees 1, 3, 5. Anything that's got an odd degree is going to behave like something linear. Let's stick with a linear one, though. So let's just draw a straight line. Positive coefficient, when we're talking about linear, that just means like a positive slope. It's going up from left to right. So a positive leading coefficient would look something like that, or if I was doing a cubic one, it would have that swooping kind of shape that would look like that, but they're still doing the same thing. So we're going from quadrant 3 towards quadrant 1, right? We're going this way from 3 to 1. And then the last one, odd degree negative coefficient, again, think linear, but with a negative slope. It's going, if we go from left to right, it's going from here to here. That would be from quadrant 2 to quadrant 4. I've already talked a bit about the transformation formula. You know this from grade 11. You really want to become familiar with this. You want to make this one of your best friends in math class because we're going to use it all the time. A is our vertical stretch, right? So that letter, that number that comes right after the equal sign is our vertical stretch. K is our horizontal stretch or compression. That's the one that comes inside a function but still in front of the x. D is our horizontal shift. That moves things from left to right. C is our vertical shift, moves things up and down. We'll come back to this in a minute. All right, I want to get rid of all this and do it from scratch. So let's just see if I can delete this. All right, let's just do this one together. All right, so let's graph this. So take a look at this function right here, y equals negative 2 bracket x minus 3 squared plus 8. What type of function is it? Is it linear, quadratic, cubic, whatever? Well, it's, I hope obviously, quadratic. The parent function, the basic one, would be y equals x squared. So that's what your basic quadratic looks like. If I was to graph the parent function, then you know the step pattern. We're going to start at 0, 0. We're going to follow the step pattern. We're going to go over 1, up 1, over 1, up 3, over 1, up 5, and do that on both sides. Connect the dots. Here's a decent graph of a parabola. All right. If we want to do transformations, we want to use the transformation formula. Maybe I'll write it here. I'll get rid of this for now, and I'll write the not transformation formula, the mapping formula. It's the one that goes x, y. If you've got a point, x, y, you can transform that single point by doing x over k plus d and a times y plus c. So this will let us identify, if we identify a, k, d, and c, then we can do this on a point-by-point basis to transform specific points, then connect the dots again. So if I use the same color coding that I did before, I had green for my a value, I had blue for k, but there's no k. K is a number that would be here in front of the x, but inside the brackets, that's 1. So there's really nothing there. You can either say that there's no k value or that the k value is 1. Doesn't change anything. D, I used pink. That's positive 3. Remember, inside the brackets, the d value, you always change the sign of that. And then C is positive 8. So A, D is positive 3, C, K equals 1. I'm not going to bother writing that down. So if I want to use this mapping formula, the easiest way to graph a transformation, I know that for a parabola, that one you're probably pretty familiar with. You just figure, oh, I'll flip it, I'll stretch it, I'll put the vertex at 3, 8. But this transformation type formula will help you with any shape, whether you know what it should look like or not. So let's just go through it as if we didn't know. So what we do is we start with with our parent function. Actually, I make 3 columns. I make it into a table. I make 3 columns. I call it parent, which would be some points on the graph I've already done. So remember, I started at 0, 0, and then I followed the step pattern. So we had the point 0, 0, we had the point 1, 1, we had the point 2, 4. We also had the points. I don't need all of them. Usually 5, I figure, is a good number. So maybe I'll go to -1, +1, and I'll go to -2, +4. So all I'm doing, in case you're lost, is I'm taking these 5 points that I'm highlighting in red and writing down the coordinates to them, because those are points that are on the original function. Then what I do is I just do the stretches. Now, different people like to break this down different ways. I like to break it into 2 steps where I just do the stretches as a separate step. And I just call that column stretched. And I recommend it. It seems like the easiest way to me. So I just go down and I actually stretch these points. So this first one, 0, is an x value, right? These are all x values. All right? So what do I want to do with them? Well, if I look at the transformation formula, I want to divide all my x values by k. What was k in this case? K was 1. So dividing by 1 is going to make no difference. In other words, for this particular one, I'm going to divide all these by 1, and therefore really not going to do anything to them. So I'm still going to just have 0, 1, 2, -1, and -2. Sometimes that happens. Sometimes you don't change anything. Then I have my y values. Here's the y values from my original parent function. Those are supposed to be multiplied by the a value. What did we say a was? Well, a is -2, right? So maybe I should have highlighted that in green so that you can see that it matches the -2 in the actual function. Anyway, so I'm going to multiply all my y values, all these values here, I'm going to multiply them by -2. And it doesn't take long. It's really quick once you get the swing of it. So 0 times -2 is 0. 1 times -2 is -2. -8. -2, -8. So I've just stretched them. If I wasn't explaining it, I would have done it in about 5 seconds. But, you know, I have to slow it down while I teach it. Then I'm going to do these shifts. I just call it final, this column, because this will give me my final points. And so, again, going back to the mapping formula, I'm going to take the x values from this column, and I'm going to add the d value, which was 3. So I'm going to add 3 to all those x values. So 0 plus 3 is 3. 1 plus 3 is 4. So again, if you're lost, I'm adding 3 to these. All right, I just want to undo these colors as I go along so that I don't have to do it later. 2 plus 3 is 5. Negative 1 plus 3 is 2. Negative 2 plus 3 is 1. There's my final x values. Then I'm going to finally take my c value, and I'm going to add that to all my y's from this in-between step. So I'm going to add 8 to everything. So 0 plus 8, negative 2 plus 8, negative 8 plus 8, negative 2 plus 8, and 8 plus 8. This is called I call this column final because these give me 5 final points that I can then graph, and I'll have my transformed function. So I've got the point 3, 8. Let's choose baby blue here. So I've got the point 3, 8. I've got the point 4, 6. 5, 0. 2, 6. And 1, 0. As you can see, I've got 5 points. If I connect them in a logical way, I'm going to get my same parabola shape. And it's been shifted, it's been transformed so that it now has what we'd expect. It's been reflected in the x-axis as we expected. It's been vertically stretched. It's been shifted 3 units to the right and up 8 units. And it's really precise because I use specific points. Those points, sorry, I lost my train of thought. Anyway, let's just say I know, again, that you probably are familiar with doing transformations of quadratics without having to do all of that. But what happens if you get to something like this one? It's a cubic. I won't go through this one because I don't want to make the lesson too long here. I won't go through it in detail, so I'll leave what I've already got. But let's just talk about what I've got here. The parent function is y equals x to the 3 because that's what this looks like here. It's got that exponent 3. Now this one's a little bit different. It's not a polynomial. Well, it is a polynomial, but it's not in standard form. But it's still, picture it, imagine that it is like the polynomials you already looked at. So it's in factored form. Let's call it that. The blue graph that I've already drawn here, maybe I'll get rid of the red one so as to, can I do that without messing everything up? Kinda. All right, this blue one is what the parent function of a cubic looks like. It's what y equals x cubed looks like. How do I know? Well, if I don't know what a graph looks like, I can always just make a table of values and plug numbers in. So if I wanted to do y equals x cubed and know what that looks like, I could use Desmos, of course, but I could put 0 in for x. And if I stick 0 in here, 0 cubed is still 0. I could put 1 in here, and 1 cubed is still 1. I could put 2 in here. What's 2 cubed equal to? 2 cubed means 2 times 2 times 2. That's equal to 8. Right? Negative 1 cubed is negative 1. Negative 2 cubed is negative 8. That's where those blue points, these points that I'm highlighting or that I'm going over again, that's where they came from. That's what the parent function of a cubic looks like. So then you doing the transformation, parent, there's the 5 points just written in there in this column here, right? Then I have to look at my A, K, D, and C values. I can see that A is equal to a half. I can see that K, again, is that number inside the brackets in front of the X. It's a 1, so I can kind of ignore that one for now. But my D value is negative 1, because, again, I have to change that sign. C is negative 5. Using the mapping formula, if I go through and divide all of these X values here by 1, because that's divided by K, I get these. so no change. If I multiply all my y values by a, which was a half, then I'm going to get half of negative 8 is negative 4. Half of negative 1 is negative a half, so on. Then I'm going to do my d value, where I'm going to take all of these things, these numbers here, and subtract 1, or add negative 1 to them. That's where these numbers come from. Then I'm going to take all my y values here, and I'm going to add c to each of them. So I'm going to add negative 5, or I'm going to subtract 5. That's where all these numbers come from. When I do that, once I'm done, these are my final points. These 5 points are on my transformed function. So then I plot them, negative 3, negative 9. Negative 2, negative 5.5. That was one point I wasn't able to delete before. Negative 1, negative 5. 0, negative 4.5, and 1, negative 1. The shape will remain the same. So that swoop that was in my original blue one is still going to be here. So I can use that as a guide and know that if I connect the dots in this way, it's still got the same shape, but it's just been shifted down. It's been shifted to the left. It's been compressed in half. There's my transformation. I didn't talk about the domain and range, so let me backtrack to this one for a second. So I want the domain and range of the light blue. Well, it's a parabola. The domain is all real numbers. The range is all real numbers that are less than the vertex, so less than positive 8. So it's real numbers, but y has to be less than, not like greater than, less than or equal to positive 8. The domain for this cubic is all real numbers. The range is all real numbers because it goes left and right forever, it goes up and down forever, everything's allowed. I won't talk through this last one because I feel the lesson's been long enough, but take a look. The degree is 4 for this one. The parent function is y equals x to the 4. I can see what that graph looks like by, again, either using Desmos or doing a table of values like I did above to get this graph that I've done in blue for my parent function. I then took 5 points from that blue graph to put in the left column of my table, identified A, K, D, and C. There is one twist that I should point out for this one, and that is, this is an important one, look what I'm highlighting here in green. You can see that there is a K value, which is a half, and that it looks like the D value is positive 1. But that's a trap, because K value should always be factored out from the D value. So if you look below that 1/2, I just wrote it as a 0.5, and when I factored it out, put x minus 1 in brackets, factored it out, when I divide that 1 by a half, it actually gives me a 2 here. So my D value isn't positive 1, my D value is actually positive 2 because I had to factor out K. That's an important one. But beyond that, there's my A, K, D, and C. Use the mapping formula to do the stretch and the final. Plot it, you'll get it in red, and there it is.